facility, ADDFab. For those of you who do not know me, I am Lisa Korpieski, the Director of Communications and Marketing here at the Institute for Applied Life Sciences. In today's seminar, you will be hearing from David Follette, the Director of ADDFab, as well as our guest speaker, Meghan Huber, an Assistant Professor in the Department of Mechanical and Industrial Engineering here at UMass. We are hoping that with these bi-weekly seminars, you will discover what great resources that the centralized UMass core facilities offer to our campus community and the New England region. So I just want to go over a few housekeeping items. This seminar is being recorded. If you miss any part of the seminar or would like to forward it to someone who could not attend, there will be a replay of all of this and the previous seminars in the series on our website. We will put the link in the chat for you. I recommend you set your view mode to speaker. Please stay muted during the talks. At the end, we are going to save the Q&A at the end of the presentations. During this time, I welcome you to use the raised hand feature. Once called upon, please unmute yourself and ask your question. Also, you can put your questions into the chat, know who they will be addressed to, and they will be read for you. Thank you. Next up, I would like to introduce you to Andrew Bernard, the Director of our UMass Amherst core facilities. Andrew?
Thank you, Lisa. Good afternoon, everyone. Thank you for joining us for the third core seminar. My name is Andrew Bernard, and I'm the Director of the Centralized Core Facilities here at UMass Amherst. The goal of this core seminar series is to both educate our research community about the robust capabilities available and to hear from our partners and expert users who appreciate the importance of these invaluable resources. The UMass core facilities are open to anyone from undergrads through senior scientists, regardless of affiliation, including researchers from other academic institutions and commercial partners. From sending samples for analysis or designs to be 3D printed to becoming a trained user, there are ample opportunities for engagement. Though the facility you will hear from today has advanced in its name, it is genuinely approachable no matter your level of expertise. Additionally, there are many opportunities to fund your work in the course. For UMass users, there are several seed funding programs, including some now in development we hope to roll out soon, and core credits are available to all IELTS faculty members. For our external users, the Mass Innovation Voucher Program subsidizes usage for small companies based in Massachusetts up to 75%. Over the last 2 years, the 5 UMass campuses have awarded more than 400 vouchers worth more than $5 million. We are here to be your partner and to help grow the research capabilities at UMass. Please feel free to reach out to me or directly to any of the core facilities if you have questions or would like more information. Now it is my pleasure to introduce the Advanced Digital Design and Fabrication Facility known as ADDFab. ADDFab is led by founding faculty director, Dr. Sundar Krishnamurthy, and Dave Follette. Dave joined us a little more than 3 years ago after working with Carbon 3D, a Silicon Valley startup that utilizes 3D printing for consumer products, including a partnership with Adidas to print shoes. Dave's combination of an engineering degree and an MBA, in addition to his experience in industry, make him uniquely suited to head up this facility. He has been involved in every aspect of operations, from training students to design engineering to business development. We are grateful for Dave, and the facility's success is due to his hard work. With that, I'll pass it over to Dave, and will be available during the Q&A. Thank you.
Great. Thank you very much, Andrew. Thank you all for coming today. I know everybody's busy these days, balancing being at home, trying to do things over the web. I really appreciate you coming, and I hope we can teach you a little bit about ADDFab today. My background has some of the parts I normally show off when we do events like this. I really like to pass parts around because 3D printing is really about making real things. But unfortunately, this is what you get for today. So enjoy the background and feel free to ask questions about them later, about any of those or about anything you hear as we go over it. So they asked for a title for today's presentation, and I was trying to think of something a little bit different than what we usually talk about. So I wanted to think of 3D printing as what I call a multi-tool for research and manufacturing, mostly to help you think, kind of broaden your mind about how 3D printing works. I think a lot of people think of 3D printing as being just fun and for toys, and there is a certain element of that. So like this multi-tool, it's shaped like a bike. You know, it's kind of cool. Maybe it's a gift. It's kind of novel. But you dig a little deeper, and this bike multi-tool has lots of different tools kind of built into it that you can use. You might also think that this tool is only, for engineers, 3D printing, and it does only these very specialized things. But what I want to share is that we've had users, all over campus, from people doing different kinds of art to people building bridges in concrete to people actually off campus doing architecture projects, and we have even people in the psychology department doing 3D printing. So beyond that, people aren't just printing prototypes either. They're printing real, I'll say, end-use parts or for production. We have quite a few small businesses that are not doing huge volumes of production and actually can print high enough quality parts such that they can ship those as things that they're selling. So that's a great opportunity as well. Like this tool that we're looking at here, another application for 3D printing is kind of for tooling or holders or fixturing, things that help you do the end product. So if you're thinking, oh, I wish this thing had a different handle, or I just had something that could hold this microscope slide at a certain angle, my life would be so much easier. We've done so many projects like that that are kind of one-off little custom things that really improve the way people work and is a really good application for 3D printing. So we have lots of different materials that we'll talk about, lots of flexibility in design. And our goal is to help you take advantage of this 3D printing and additive manufacturing tools and hope that you can think about them in much broader ways than just kind of a toy or just a prototype. So with that kind of intro, I want to talk about our technology just a little bit. So we print in all kinds of things, all kinds of different materials. You're probably familiar with a MakerBot that's kind of like a hot glue gun that moves around and prints in kind of a weak multicolored plastic. We have much higher quality polymers, mostly nylons that are very strong, very resilient, very accurate. We even print in metals, primarily steels and nickel alloys, but we can talk about other metals that you may be interested in. And I mean, the other things we do are really bringing expertise to 3D printing. So there's a lot of help we can provide in getting your design ready, understanding what can and can't be done with 3D printing. And we even do a lot of training. So there's help for undergraduate and graduate courses, as well as workshops that we do their hands-on for local businesses and industry. So kind of our goals, we try really hard to be accessible, certainly to everyone on campus as much as we can, even during the pandemic, and to businesses in the area. And we want to be effective. So sometimes that means getting parts out in a matter of hours. And sometimes that means printing something that you're not really sure if it's going to work, or it may take a few tries. You probably wouldn't feel comfortable just submitting it to someone online, but we can then kind of work through it to make sure it works. So here are some examples of the things we print. We have an interesting multi-material printer, so you can have rigid and flexible things in one. And we even have one that can put carbon fiber into the part to get some really incredibly strong plastic parts. So I want to talk about a couple of examples of people we worked with and projects that went really well. So one of them was with Professor Adam Grable in psychology. You might say, psychology, 3D printing, how do those go together? So what he's working on is a tantrum detector. So those are children, what if you could predict a tantrum before it came on? That would be interesting. So he has a custom, almost like a Fitbit that you wear that monitors biometric signals. And can, not yet, but the goal is to take lots of data and then understand when tantrums happen. So that's great. Maybe we could give kids just this ugly looking watch and they could wear it. But his idea was, what if we can have different colors, different designs? How do we get kids to want to wear this watch? So what we did was had actually some of my summer interns design a bunch of different face plates and a nice enclosure that takes the kind of boring circuit board and puts it in a fun enclosure for kids. It's interchangeable, so they can change every week or as a reward for wearing it or whatever. That's the psychology part, not the engineering part. And then we were able to deliver a whole array of these. And say, Pokemon goes out of style. Easy, we just print something else. We can print whatever character is in style today. So I really liked how we integrated an off-the-shelf watch band into that. So you could have kind of the texture of a watch band that you want, but then put all this together. So that's been a great project and continues today as he adds more and more children to his testing. On the industry side, also UMass though, Clarity Water is a startup that came out of UMass. And we've been doing a bunch of printing for them, kind of to show both sides. The colored pieces in the center, those you can see in the arrow. It's a little bit harder to see, but at their booth, that is a demonstration of the parts. So they're colored, so you can identify which are which, point them out clearly. They're not functional, but nice for a demo. On the right are actual functional parts. So one of them is actually printed in stainless steel. You know, Barrett called me, the CEO, and says, you know, our offshore supplier can't deliver this part fast enough. I need it in a week. So sure, we can print your parts. That's something we do. So we printed him 2 in a couple of days, and he had parts he could use. So we could build this whole thing in a very short period of time. And even though it's cheaper to go offshore and get things at maybe higher volumes, when you need it now, we can certainly help work that out for you. So that was a great success there. And they continue to print more parts. He actually emailed me about 30 minutes ago and said, hey, you still open during COVID? The answer to that question is yes, we are open. We've been printing pretty much the whole time, even some things to support COVID. So support the PPE efforts to combat COVID. So that's actually all for me. My piece is pretty short today, but I would be happy to discuss more things, particularly your project, anything you're interested in. On the topic of COVID, we can talk about this more. One of the projects we did do is work with a local company in prototyping a new type of N95 mask that's both reusable and inexpensive. So we can talk about that. If you have more questions, feel free to contact me. And at this point, I would like to turn it over to our invited speaker, Professor Meghan Huber, who I actually interviewed when she came maybe over a year ago. And then she started in January and then right into stay-at-home orders. And we first started working together actually virtually over Microsoft Teams quite a bit. And Meghan got right into ADDFab and was able to use some of our tools to work on a very interesting project to support PPE for COVID. So she has quite an impressive resume. I'll let you read it there, but she now has the Human Robot Systems group in the mechanical engineering department and uses lots of 3D printing as well. So she will tell you a little bit about her research. And so I'll turn it over to you, Meghan. Thank you very much.
Thank you, Dave, and thank you for having me. So I'm going to go ahead and share my screen here and talk to you all a little bit today about how I am using 3D printing in my own research and also in some of the COVID-related responses that the university has been doing over the past months. So the title of my talk today is Designing and Manufacturing Human Wearables. That's a very broad topic on purpose because I'll cover several different things. But you should know that my main research here at UMass is in human robot systems, and particularly I head up the Human Robot System Laboratory. Our mission is to advance how humans and robots learn to guide the physical interactive behavior of one another. To do this, we do have a lot of different projects. The first is we develop new methods of quantifying or representing human behavior that are compatible with robot control, understand and improve how humans learn models of robot behaviors. When you look at a robot, how do you know what it's going to actually do, and how can a robot communicate to the human effectively? And then we also develop robot hardware and controllers in order to enhance robot physical interactions with the humans. And so this is highly interdisciplinary work, and it lies at the intersection of a bunch of different fields, including robotics, dynamics, controls, neuroscience, biomechanics. And to give you a sense of the projects that better sense of the projects that we work on, here I have just a bunch of videos showing the kind of stuff that we do. So on the very left here, we have, this is a human interacting with a robot, and we're doing things like measuring muscle activation. Here we have a robot that is moving and it's doing its own thing, but how do we control these robots such that they are safe around humans? And so we can take them out of the cages where they're typically used in manufacturing settings and then put them in more the real world or in human environments. We also do things, some fun experiments where we try to say, well, if a human had robot mechanics, how would it behave and how would it control, do things like maintain balance or many of the other activities or tasks that humans can do, but robots currently cannot. We also look at human-robot interaction in terms of wearable robotics, so exoskeleton devices, as you see this student here. Lastly, we have fun, but on a more serious note, we study the visual perception of human movement, so how do we perceive and learn from the movements of other humans, but also how do we learn from the movements of robotic systems. And so today I'm going to focus particularly on wearables, so more of the exoskeleton type robotic systems. But honestly, I'm not actually going to talk a lot about robots, but I'm really going to talk about how do we actually create interfaces between, say, machines or some other type of system and the human. And so additive manufacturing, which has blown up in terms of popularity over the past years. I mean, I think back to my college years, and we had no such thing as 3D printing. And it's really been amazing. It's been allowed for the personalization and rapid prototyping of many different systems, but especially in the human wearable domain. And so, for example, you see this is actually a low-cost arm exoskeleton. This was developed here at UMass by Professor Frank Supp. It's been used to develop finger prosthetics, even commercial systems or companies. So this is an exoskeleton that I've been using from Samsung. Also includes parts that were 3D printed, again, allowing for customization. And there's also some really cool things, kind of as Dave mentioned before, people are wearing, making things that are more like art, so wearable art, 3D printed shoes. I assume it's for art purposes because those look terribly uncomfortable. And then there's also people doing some really cool things kind of at the frontier of additive manufacturing, developing flexible electronics. And so here you have 3D printing of conductive ink on top of flexible materials. And this is out of a group from the Beast Institute in Harvard. And so while there's a lot of opportunity and advancements in human wearable technology, there's still a major challenge. And this challenge is, I would say, it's not a technology problem. It's something that even if you have, or that we've been dealing with for, I would argue, probably hundreds or maybe even thousands of years. And that is developing things to interface with the human body. The perfect example here I have up on the left, sneakers. I assume everyone in their life has experienced a blister, and yet I don't know how many billions of dollars the shoe industry is, but I imagine Nike has a lot of money, and yet we can make really fast shoes. We can break 2 hours in the marathon, but we can't make shoes that don't give you blisters. We still have trouble making, say, pants or garments that stay up regardless of your body type. Or even if we develop materials or items of clothing, such as gloves, that do what they're supposed to, such as, say, keep your hands warm, they can have unintended consequences. For instance, if you've ever worn ski gloves and tried to do any type of fine manipulation tasks, you'd probably find it very challenging. And so a lot of these same challenges that we have just in developing everyday consumer products, these also exist in the research world. So whether it's developing a prosthetic to fit onto a amputated limb without creating pressure points, how it's designing an exoskeleton that doesn't slip throughout the day as you're actuating or applying force onto, say, a cuff. And even spacesuits, right? How are astronauts able to perform manipulation tasks when they have these big, bulky suits on? So interfacing with the human body is just a universally challenging problem across many different levels of technology and different fields. And so today I'm going to briefly talk about 3 different topics in manufacturing and designing human wearables. The first is 3D printing meshes to mimic biological tissue mechanics. I'm going to also talk a little bit about slip-proof exoskeleton cuffs. And then lastly, I'm going to talk about the face shield project, which we performed in the ADDFab lab over the last few months. So typically when we think of 3D printing, or at least how I used to think of 3D printing, was things like this. As kind of Dave mentioned, little toys, hobby items, rigid, hard plastics. And it wasn't until I got involved in this project that I realized there was so much more. And so here we have 3D printed meshes. And the goal of the project was to be able to mimic certain aspects of tissue mechanics, specifically the anisotropy of these tissues. So meaning that they have different stiffnesses depending on the direction that you pull on. And so here's just an example of a mesh that we have created. This was work done at MIT during my postdoc. And so you can see here, basically we have a mesh and you see these little waves here. And basically what that is 3D printed slack. So I'll see if you can see in my screen, we'll do a live demo here of one of these meshes. But you can see in the direction where you see the waves, as I'm pulling, I can pull pretty far, great change in length. However, it's much stiffer if I'm pulling in this direction. And so depending on which direction you put waves, how many waves, how thick the material is of the waves, you can get really cool different behaviors. And just to demonstrate how similar we can get the mechanics of this 3D printed mesh to, say, biological tissue, here I have stress strain curves for rat muscle. So those are the dashed lines. And then here I have one of our 3D printed meshes. And you can see that if you properly choose things like the amount of 3D slack that amount of slack that you're adding into the, say, parallel direction, and including the perpendicular, you can see there's a little bit of slack there. You can actually quite nicely not only just mimic the tissue mechanics in terms of the magnitude, but also in terms of the linearity or non-linearity specifically. In addition, you can also do things like you can add 3D printed, or you can add other materials in between your 3D printing. So for example, here shown in figure D, we've actually added in steel thread. And so what that does is now you can create these really nonlinear responses such that you can be really, really flexible, but as soon as you hit, say, a certain limit, now all of a sudden your mesh will become, I don't want to say infinitely, but very, very stiff, right? And so that's kind of explained here in this blue curve. So you see the strain that's responsible from stretching the elastomer or the 3D printed material, and then you have the response that's coming in from the steel thread. And so there's many applications for this, including implantable devices. But what we were really interested in doing was actually thinking about how we could use our meshes in order to assist with rehabilitation from ankle injury. So I don't know if any of you have ever sprained your ankle before, but it's very common. And typically what happens is when you sprain your ankle, you have over-inverted your ankle. So you've gone like this and strained your muscles. And so if you have experienced such an injury, you'll be put in a cast like this, not necessarily the plaster casts, but something like this air cast. You'll be allowed, you can still, once the injury is healed, you can still perform whatever sports you want to, but generally what happens is that your muscles are weakened. And so you typically end up wearing a brace, something like this, that provides rigid support and essentially prevents you from rotating that ankle or using those injured muscles. Oops. However, As I'm sure many of us know, especially during quarantine, if you don't go to the gym, if you're not using your muscles, you lose them. So one of the issues with a cast like this or with an orthotic like this is that because you're preventing ankle movement, those muscles that you actually need are atrophying. So we decided to use this mesh and see if we could come up with something that would allow humans to use or control their ankle, so you could still move your ankle in inversion and eversion. But once you get to a certain limit, we don't want you to be injured, so then the device will actually kick in for assistance. And so what we have is something like this. Now, basically, it's this white strip that you see here. Ignore this big black bulky thing that you see in the picture. This is a robot that we use to measure how well the robot or the mesh works. But essentially it's something like this. Again, follows the very same pattern that I had talked about, where you have lower stiffness in this direction, you have high stiffness here, and we have introduced a nonlinear response. And so just to give you a quick idea of what that looks like, in black, we're looking specifically at the inversion direction. And so here you have your displacement torque curve. If you took the slope of that, that would be like your stiffness or linear stiffness. And what you see in black is a subject, their ankle stiffness in the inversion direction without the material. And then what you see with blue is with the material added. And so in this little peanut-shaped diagram, you can see that actually we're only adding stiffness to the inversion direction right here. The stiffness values all match up pretty much everywhere else. In addition, if you were to take the difference between these two curves and the figure in panel C, you would see that we are adding nonlinear stiffness here. So essentially, this is just saying that our material is doing exactly what we want it to do. So now to switch gears just a little bit, so to more, I would argue, maybe more traditional 3D printing. One of the things that we, especially in working with this project, whether it's attaching a brace or an exoskeleton cuff, is the fact that when you are pulling on these materials, you can create an unbalanced shear force that can result in the motion of whatever attachment or body anchor you have on the human to move. So think about it this way. Imagine you're wearing a pair of socks, and if I pull on those socks, if there's not enough shear force to counteract that, the sock is simply gonna fall off, and it's not actually gonna transmit force to the body. And this is a common problem in exoskeleton design. And it's exacerbated by the fact that if you look at limb geometry generally, you become thinner, so your geometry tends to decrease as you move away from the body, which is bad, right? So think about this. This is a setup here, but you can imagine if this wooden thing, if that's say your leg, and you have this cuff here, you can imagine that if you start to slip a little bit, that thing is coming right off. So we wanted to design a cuff that would allow, that would actually vary how much it's compressing around your limb in order to increase shear force acting against whatever force, say, an exoskeleton actuator is applying. And so essentially it's going to tighten up when it wants to apply a large force, but if it's not applying any force to you, it's going to relax. So it's also not uncomfortable. And so this is just a quick setup. And here I'm just going to play a few videos just to kind of show you the mechanism. And what's manufactured here is, you see, this is the cuff. This is just neoprene fabric. And here, this is a mechanism that's printed with carbon fiber. It's using the Mark Forge printer, which even though we didn't print this in ADDFab, is available at ADDFab. And I might be a little biased, but I would recommend if you want to 3D print anything of quality, that's one of the ones to go for. So this is using their onyx material. And so what you can see here is that the limb is moving up and down. And if you look closely, you can see that these wires are tightening around the limb as I'm applying a force downward. And essentially, these wires are all connected and arranged such that there's minimal force actually being exerted onto the box. So it really acts like essentially a lasso. And to give you some perspective is that if we were to take that same mechanism and we were to add this screw, which essentially locks these wires and prevents them from compressing around the limb. I'll kind of, whoops, fast forward this one a little bit. It looks like it's kind of slow-mo or like nothing's happening, but what you actually see is the limb is moving and the cuff is just slipping right off the limb, showing that really this variable compression mechanism is actually improving how an exoskeleton can attach to the leg. And just to kind of switch gears very quickly, I just wanted to talk about the face shield project. So I'm sure like many of you, 2020 was an interesting year. I joined in January, and so I was working on some of these projects with the exoskeleton cuff and the 3D mesh. And then we got that call in March that we were going virtual and everything was shut down. And so even as we were preparing classes or trying to figure out what to do with research, I mean, there was a lot of calls on TV and in the news for assistance in developing PPE, given the worldwide shortage. And it was specifically this down here, this program on CNN, and there was a doctor from MGH on TV saying, we need 3D printed masks. And several of us from UMass, Dave and Professor Frank Supp, also from MIE, we were like, well, we have a lot of 3D printers here on campus. What can we actually print or make? Well, it turns out we decided to go ahead and develop a face shield. Now, a traditional face shield looks something like this. I'm sure many of you have now seen or probably didn't know what it was before, but do now. So plastic sheet, it has a foam band, and then you have a non-latex elastic material that essentially wraps around the head and holds it tight. The problem is that, you know, you can, again, think back to March when you could barely get toilet paper. You know, how are you actually going to be able to sort plastic and foam and this elastic material? So we wanted to develop a face shield that was only one material so we could avoid any bottlenecks. We wanted to make it low cost such that it could be disposable. And we wanted to scale to be able to meet the demand. So while 3D printing is great, takes a lot of time and money to make pieces. So you have to think about what exactly it is that you want to manufacture and what is the best method. In addition, we also wanted it to be recyclable because we sure are using a lot of plastic in these times. And so just quickly, it was very much very interesting and enjoyable experience. Went from prototyping all in our own homes and meeting over Teams. This here is a book cover that I bought at Staples. I also have a vinyl cutter at home, so I was cutting little mini masks and testing them on my wine bottles and beer bottles at home. And then we actually came in and started working in the ADDFab lab. So here, this is Asma Jane, one of the students who's working in the lab. And we laser cut. These are a whole bunch of face shields that we laser cut. And then we had a really amazing team. You'll see in a minute, I'll show everybody's pictures. Clinical team that was able to provide us feedback on our designs. And so just quickly to give you an idea of what this face shield looks like, it's a single piece of plastic. You fold the flap. Turns out I have several in I have a bunch in my office, so if anybody needs face shields. But looks something like this. It's generally quite easy to put on. And you're done. So as part of this project, we had, thanks to generous funding from ISLES, donated 90,000 face shields. While we prototyped within ADDFab lab, we ultimately moved to using another manufacturer in Southbridge, Massachusetts, to over 90 facilities with contactless pickup, and they went all over the state. And so that brings us to 2020 now. And so I thought I would leave you all with this parting message. You know, as I mentioned when I started this project in March, this is essentially what I looked like. But being involved in the face shield project, really, I felt gave me a sense of purpose over the past few months. And for anybody who is feeling like this in August, or has students who feel like this, I would just say that either you should or encourage others to make something and to add something positive into the world. And so with that, as I mentioned, we had a huge team involved in the face shield project. Even though it was just a single piece of plastic, it was actually quite complicated and couldn't have accomplished anything without this big team of people. And here is the contributors and funders for some of my other exoskeleton work that I presented earlier. And so with that, I think we are going to take some questions.
Thank you so much, Megan. That was so informative. So does anybody have any questions? You can put your hand up. You can unmute yourself and just ask your question. No questions?
I have one.
Okay.
Will you be working with the Human Subjects Lab also?
Yes. So, I mean, honestly, one of the things that actually, as Dave mentioned, you know, on my interview around campus, one of the things that really drew me to UMass in general was the fact that we have all of these core facilities. And so even if I have a 3D printer in my lab or a motion capture system, there's a lot of things that even in my own lab that I couldn't do without that. So yeah, so honestly, plans to use I guess we can do human subject now. We're trying to be a bit safe, but absolutely.
Anybody else? I think Dave, you have some things you wanted to demo or show?
Sure. It's always fun to show stuff. So I was looking around what I have at home. You know, during the pandemic, I brought the Markforged home, actually. The day they said you need to work from home, I was like, grab anything I can and take it.
So is that your favorite 3D printer at the moment? Like,
so the Markforged Onyx is my favorite. I might have to turn off the background, but to see my world here at my house. No background, here we go. Okay. So I made this out of Onyx. It's kind of cool. It's a demonstration of a clock mechanism. So it has a hairspring over here, it has a wind-up spring over here. All these parts are 3D printed based on an internet design, but this was helping us understand harmonic motion for a project that we did with CS. You know, you don't think of computer science faculty doing a lot of mechanical things or even 3D printing, but we have worked with them quite a bit. So that was a fun one. One more I'll share is we have a customer who wanted to design their own Frisbee with very specific shape. So we cut an existing Frisbee and then have 3D printed something that's very similar in shape. So we can do these little samples and then compare how the rim matches, and you would be surprised, like very little changes along this leading edge affects how the air flows over it and the Frisbee flows differently. Helps to have played some ultimate Frisbee in college and really like be comfortable with Frisbee, but this is another fun one that I can work on from home. And yeah.
Yeah, I will say, especially thinking more towards you know, the future, or even in my own lab and my research. I mean, the question asked about human subject testing. I mean, my lab, it's hard to do any of that type of research at the moment. So thinking about how one can engage students, whether it's your own research students or in the classroom. I was up until recently a postdoc, so I understand that, like, you know, writing papers all day can be very, very boring, especially when you have to do it alone. So just thinking about activities or say parts of your research that can involve some design and can be fun and be a way to kind of break up the monotony. And you don't have to be an expert to do this. I will say up until like January, 2020, I don't think I had ever, I had sent files to somebody to print, but had never actually even printed anything on my own. And look, and there's plenty that you can do. So I would just, encourage you or your students to think about how, you can actually have some fun and incorporate design into your work.
We have a question from Karen.
Hi, so I always have startups on my mind, and but I think this question applies to faculty too. What would I need to do to be, if I had some idea of something I wanted to print, what would I need to come to you with before I could really fit into your workflow?
So that's an excellent question. We actually do that quite a bit. A lot of the work at ADDFab is from outside, and a lot of those outside companies are small. I guess Andrew talked a little bit about the voucher program, so there are ways that the state can help out with reducing the cost. But in terms of printing something, we work with people with a whole range. Some are, they're like, I've got my design, here is the STL file, I want this material and like this, and please just print it. That's great. We have other people who just come with a napkin or less than a napkin, and we just talk about what they want to do. And then we actually do all the design for them. So that project with the watch bands, they didn't have any CAD design to start with. So we started from a clean slate and basically just an electronics board that they wanted to attach to a child. We started from there. So really, we can provide the whole range anywhere where you are in that spectrum. We can certainly help out. And it's also an iterative process. So we can start down one path and then pick something else. We can try different things. There's a lot of flexibility.
Okay, thanks.
Any other questions?
Yeah, I was just wondering if there are any plans to get new printers, and if there were anything that you were looking into for new materials.
Sure, that's a great question. We got a bunch of printers initially when LSL, IELTS, it was all started. And since then we've invested, I guess we've bought a couple of different printers. But generally the impetus to buy a new printer comes from users. So someone like you would say, hey Dave, if we just had this printer, look what I could do. I would use it so much and everybody would be so happy. Then I can go and make the case saying, oh, look, there are these people, they really want this printer, and we can work on getting that. I think we have some areas that we could improve on. One of the things that I hear people wanting, but there's not this desperate need, is certainly around clear materials. So if you want to see inside what you've printed, we have some clear materials that are more like wax paper, clear, not like glass. There's that area. I think a lot of people have been interested in microfluidics. So we have some applications in for grants to get what's called a nanoscribe. It prints like in a centimeter cubed volume. You can print the Eiffel Tower very, very small. Very specific for certain things, but certainly useful. There's also a grant in for a glass etching type printer, which would help with microfluidics as well. We also do, or have done in the past, the lunch and learns. So if you want to email me, I can add you to our list. And we bring in a manufacturer from the outside, and they'll talk about their printer and why it's so great and what new things it can do. So everyone get an idea of what's available, and then we can decide if that's something we want to add or not.
Anybody
Yeah,
else?
just to say, I feel like getting involved and doing some 3D printing, it does really open your eyes to what manufacturing is like, right? And what are the techniques that are currently being used? So really, I view 3D printing as, I mean, on one hand, a very important research tool, and there's a lot of innovations that you can do within 3D printing itself, but also thinking about it as opening the doors to this whole other world of manufacturing that's usually kind of shielded from us.
Thank you so much for answering my question. Can I ask another one? Do you only work with material extrusion printers, or are you, I'm not sure if you already said this, but like, are there VAT photopolymerization or anything like that?
Oh, an excellent question, and some really good, I'll say, key terms. VAT photopolymerization is like the correct term. I don't hear it that often. Most people call it SLA, I think. But we do have a bunch of different technologies. So the Markforged we were talking about is extrusion. People call FDM or FFF, sort of a tissues versus Kleenex thing. So to go through kind of what we have, there is FDM with the Markforged. There is SLS, which is selective laser sintering, which is a nylon powder-based system. So it uses a laser to sinter tiny bits of powder into a solid to get you a very nice, very accurate parts without supports that are generally required with FDM or extrusion systems. We also have a Stratasys Objet, which is kind of like SLA in that it uses a UV curable resin, but it also uses like an inkjet printer and then jets out that curable ink and then uses UV light to cure it. On the metal side, we have a direct metal laser sintering, which is again laser powder, which is powder plus laser, so metal powder sintered with a laser. Then we have one more printer that is directed energy deposition, so it blows metal powder at a laser, and then you draw lines in metal. To answer your question, we do not have a VAT photopolymerization or SLA printer. Those actually do pretty well for the clear materials. I used to work at Carbon 3D, which is kind of it's an upside down version of an SLA printer. And it is something we're considering. One of the challenges with SLA is since your part goes into this bath, you have to have about $50,000 of material in the bath just to start, no matter how big of a part you're building. So it's always a question of cost and use and trying to figure out what the right balance is there. Does that answer your question?
Yes, thank you very much.
Anybody else? Okay, I guess we're all set. So I want to thank everybody for attending today's seminar. And thank you to Dave and Megan. Those are really informative talks. Throughout the series, we're going to be featuring individual core facilities and the relevant technologies. Our next seminar is scheduled for Tuesday, September 8th, in which we will be sharing a short overview of the centralized UMass core facilities' new administrative management tool, Quorum, which will be used for all scheduling, tracking, and billing purposes. We are hoping with this session we will familiarize users with the new system and answer any questions you may have. So save the date and we hope to see you there. Goodbye, everybody, and thank you for coming.